Hi, this talk is about testable properties in general graphs and random order streaming. I am Hendrik and this is joint work with Arthur, Pan and Christian. Let me start this introduction by introducing you to property testing. Consider any decision problem, for example, a problem on graphs like planarity. And if you think about the computational complexity of deciding planarity and a few examples, you might come up with these. For example, the graph on the left, which is clearly planar. This graph here, which is, well, almost planar. The graph here, which, well, is easily recognizable as non-planar. And this graph here, which is definitely not planar. Now, we know that the time complexity to decide planarity is at least linear in the size of the graph, in the number of vertices. And if you think about why this is the case, well, you might conclude that it's because of this, well, almost planar but not exactly planar case. Here it's really hard to spot the one edge which makes this graph non-planar. You could consider these three graphs which are not planar as, well, slightly non-planar, quite non-planar, and very non-planar. And the lower bound is because of the slightly non-planar graphs, intuitively. Now, if you wanted to overcome this lower bound, one thing you might want to do is to relax the problem. And how would you relax it? Well, by relaxing the cases which are hard. For example, here, this is the slightly non-planar case. And you might relax it in a way that says, okay, I have an algorithm which should test planarity. It should detect planar graphs. It should detect very non-planar graphs. Well, it should probably detect quite non-planar graphs, but slightly non-planar graphs, it may answer arbitrarily. So this is a relaxation. For slightly non-planar graphs, this algorithm doesn't need to be. Now, if you want to formalize this slightly and quite and very non-planar, let's introduce an edit distance. We will consider the number of edge edits, so inserting an edge or deleting an edge, that are necessary to make a graph planar, normalized by the size of the graph, which we measure by the number of vertices plus the number of edges. And now we choose our relaxation parameter epsilon between 0 and 1, and we require our algorithm to accept graphs which have edit distance 0 to our property, in this case planarity, and we require it to reject graphs which have edit distance more than epsilon to the property with probability more than 2/3. So this is what we call a one-sided error property tester. There are also two-sided error property testers, and the difference is that for two-sided error property testers, we don't require that it always accepts graphs which have the property, but it only accepts them in 2/3 of the cases. And let's introduce a little bit of notation. If a graph has edit distance at most epsilon to a property, we call it epsilon close. So even planar graphs are epsilon close to being planar. And if that's not the case, we call it epsilon far. And the complexity of a property tester is the number of queries to the data structure. And the reason why we consider this is that we actually are interested in not reading the whole input. We want to read a sublinear amount of the input, and that's what we really care about. So we measure the complexity of a property tester by the number of queries to the data structure. What's the data structure? Well, here it's really important to formalize the model the input is given in. For example, we can consider the bounded degree model, which means that we are given a graph and the maximum vertex degree is a constant, which we call d. And here the input structure is just adjacency lists. So if an algorithm wants to query a graph in this model, it queries adjacency lists, and one entry is basically one query. So if an algorithm asks for the third neighbor of a vertex v, then this is one query. And for now, let's just consider one-sided error property testers. Maybe surprisingly, many problems are actually testable with constant query complexity and one-sided error, for example, degree regularity or subgraph freeness or connectivity. There are some properties where we know that the query complexity we require in this model is sublinear but not constant, and that's, for example, 2-colorability or expansion. And for example, for 3-colorability, we know that the number of queries we require is linear in n. In this talk, I'll focus on the case where we have a constant query complexity, which means that the query complexity doesn't depend on the size of the graph at all. And to take a closer look at these properties, let me introduce one definition. And this is the definition of Q-disks or Q-hop neighborhoods. I'll call them Q-disks. The Q-disk of a vertex V is the unlabeled subgraph that is induced by a BFS that starts at V and that has depth Q. So for example, if you consider the red vertex, then the one disk of this vertex is this graph, which is induced by the red and the blue vertices, and the two disk of the red vertex is the graph which is induced by the red, the blue, and the green vertices. There's one result by Goldreich and Ron, and implicitly this is also observed by others, that says that a property tester for bounded degree graphs with constant query complexity Q can be transformed in a canonical algorithm that does the following. It obtains a uniform sample S of roughly Q many Q disks from the graph. So it samples Q many vertices and performs BFS of depth Q. And then it rejects if and only if this set of Q many Q disks S is from a family of forbidden sets of Q disks. So for example, if the property we are testing is the property contains at most one triangle and our tester sees two triangles, it rejects, otherwise it accepts. The bounded degree model is nice, especially its analysis is nice, but let's consider a slightly more general model. In particular, let us remove the constraint that all the graphs have bounded degree. Let's just consider any graph. In this model, the property tester might query the graph by querying for a random entry from adjacency lists. So what can a property tester in this model do? It definitely can't do a BFS because there might be vertices that have linear degree, and therefore querying all the neighbors of these vertices already requires linear number of queries. What it can do is to do something like a random BFS or subsampling BFS, which means it samples a constant number of neighbors and then it recurses only into these neighbors and samples a constant number of random neighbors of these vertices, and so on and so on. This means that the tester obtains at most Q many Q disks that have bounded degree at most Q. Because if Q is the query complexity, it can query at most Q many vertices, it can query at most Q many neighbors, and it can query at most depth Q. What is the difference between the bounded degree model and this model? So say that our property tester samples these two K-disks, the blue K-disk and the green K-disk. In the bounded degree model, we have that with high probability random Q-disks are disjoint. And this is because all vertices have only constant degree, so discovering a vertex is not that easy. And this implies that there's a bijective decomposition of the BFS subgraphs into Q-disks. So if we consider the subgraphs that are explored by the BFS, they map bijectively into sets of Q-disks. However, in general graphs, this is not so easy. Here, Q-disks may intersect, and this may lead to ambiguous decompositions. For example, if we just observe the two K-disks above, then it's not clear whether we have observed two disjoint subgraphs or whether we have observed one subgraph where the two K-disks intersect at a vertex. And this makes it hard to phrase a result like the one from the previous slide, which says that a tester rejects if and only if it sees a set of Q-disks from a family of forbidden Q-disks. Because imagine that the left case is a graph which has a property and the right case is a graph which is epsilon far from the property, and if you only get these two Q-disks, then you don't know whether you have to accept or to reject because you don't know which case you're looking at. Essentially, the problem is that two random BFS may visit the same vertex. How should we solve this problem? Well, first let's observe that this event is only likely for linear degree vertices, because intuitively, if a vertex has sublinear degree, there are not too many ways to discover this vertex. It's very unlikely that two independent BFS will discover the same vertex with sublinear degree. Luckily, there's only a constant number of vertices with linear degree. The solution we use is to assign unique colors to all high degree vertices. So now, if two Q-disks intersect, we can tell so because they will intersect at a high degree vertex, and this will be a colored vertex. So there's again a bijection between the subgraphs our tester observes and Q-disks. Before, our tester rejected if and only if it found a forbidden set of Q-disks, and now it rejects if and only if it finds a forbidden set of colored Q-disks. The colored vertices are the high degree vertices. The result that we obtain is the following. A property tester for general graphs in the random neighbor model with constant query complexity can be transformed into an algorithm that obtains a uniform sample S of colored Q-disks by performing roughly Q random BFS, and the number of colors is O of 1 because there's only a constant number of linear degree vertices. It rejects if and only if S is from a family of forbidden sets of colored Q-disks. Now, one question you might ask is, why should we care about Q-disks and not simply about forbidden subgraphs? Right? We could also phrase this theorem like it rejects if and only if it observed a subgraph from a family of forbidden subgraphs. Of course, this is possible, but for applications, it's nicer to consider Q-disks. Let us consider streams. That means the input structure is not adjacency lists, but it's a stream of edges. For example, if you want to decide again planarity, you know that you have a graph of size n, you want to decide whether it's planar, and now the edges of the graphs are given to you one by one. This may look like this. You might get all these edges one after another, and at the end of this stream of edges, you should decide whether this graph is a planar graph. Now you can take a second, you can rewind, and you can think about this, or, well, let me just tell you, this is not a planar graph. Obviously, this is an easy problem if you're allowed to store all the edges. And therefore, our objective in this model is to use less than linear space. But here's already bad news. Some problems in this model require linear space if we are considering adversarial order streams. On the other hand, this model is also trivial if the number of edges in the graph is at most O of n. One way to overcome this is to consider another model which is rather recent, and this is the random order streaming model. In this model, the order of the edges is not adversarial, but it's uniformly at random. There are some things that we know in this model, and for example, we know that we can estimate several graph parameters, like the number of connected components in general graphs, and this is a result by Peng and Zola. And for example, we also know that we can transform constant query testers for bounded degree graphs to O of log n space streaming testers. And this is a result by Monmizade, Muthukrishnan, Peng, and Zola. Now, what we would like to do is we would like to have a similar result that says that we can transform constant query testers for general graphs to O of log n space streaming testers. And let me just briefly tell you how we achieve this. The idea is the same as in the previous papers, and that is that we sample roughly Q vertices and then we simulate the BFS for these vertices in the stream. So for example, if the query tester's BFS looks like this, then we would like to simulate this BFS by just collecting the edges that belong to it from the stream. So for example, if we have sampled the yellow vertex and we see this edge, then we collect it. Now, of course, one question is, what happens if we get this edge in the stream? Well, as you can see on the left side, we should collect it, but we don't know either of its vertices. We don't know whether these two vertices are in the BFS. And since we don't know these two vertices yet, we probably discard this edge, because we can't afford to store every edge. And that's actually bad. One thing that we could do is to condition on the event that the edges are streamed level by level. Or in other words, we condition on the event that the edges are streamed in a good order. And actually we can derive a lower bound on the probability of this event, and this is constant. Now, if the edges are streamed in a good order, this means that we first get the edges from the first level of the BFS, and then we get the edges from the second level. And when we get the edges in this good order, we can bound the probabilities to see each colored Q-disk independently, and we are good. Now our second result states that every constant query property tester for general graphs in the random neighbor model with one-sided error and constant query complexity admits a O of log n space random order streaming tester. I didn't go into detail why it states one-sided error here, but let me just briefly tell you that the reason is that we can lower bound the probability of seeing a Q-disk in the stream, but we can't upper bound it. And this is also the most urgent open problem here, to obtain similar results for testers with two-sided error. Thanks for watching.